Okay, so to change things up a little bit, I figured out that I can put myself in a tropical landscape, which is a little bit weird, especially because I'm wearing a white shirt. And what's weird is that like this pin shows up, and then if I move it like outside of my shirt, it disappears. Hours of entertainment fun right there. Now the bad thing is you can't see the board behind me, so I've greeted you, we have a tropical scene, and now I got to change this or otherwise you can't see the whiteboard behind me. So let's choose, there we go, and now we're back. Yesterday I had, I did this with my Encore, and one of my kids goes, "Where are you at? Are you in your room or are you on the beach?" And I was like, "I'm in my room, it's just a backdrop, it's okay." All right, so here's where we left off yesterday. So yesterday we came up with these equations that said, okay, little g, oh come on, oh, hold on, wrong program. That would help. So yesterday we came up with, hold on, little g equals big G mass of the earth over r squared. V equals the square root of big G m over r. 4 pi squared r cubed equals big G mass times t squared. Okay? So, and then we also have kind of the mother of all equations. Hold on, I got a left hand again. Which is F equals big G m1 m2 over d squared. So, all three of these equations evolve from this equation. So that's why I said, you know, if you ask, you know, most scientists, you know, physicists, and you said, okay, hey, if you had to start all over with physics, and you could pick one equation to start with, this would probably be the one that they would want to start with. So here's the deal. So what we're going to do is want to look at how we can play all three of these equations into one big problem. So mathematically this isn't that tough, but the problem is actually inputting numbers into your calculator and then getting an answer and seeing if that answer makes sense. Okay, so what we're going to do is we're going to work one big problem, okay, and then we're going to spin that into some other things, because these equations aren't that tough. You just kind of have to get used to working with them. So here's what we've got, and so this is what you're going to have to be able to do on your assignment and on the test. Okay, so I say trust me on this one. Here's the worst thing that you can do is, and I know I can't see you all, but I can see Caden, that's it. So here's the worst thing that you can do is passively sit here, and I'm going to have Caden or somebody who's ever got good with their calculator crunch these numbers, and then you're going to sit there and go, okay, yeah, I see how they got it. And then you're going to get on this assignment, which is probably the hardest assignment you're going to have all year. And then you're going to try and do this, and you're not going to feel confident, and then you're not going to know if you got the right answers. So I beg of you, okay, play along, do these calculations, make sure you can get these answers on your calculator, because this is the time to check this, all right? Because once you get on this assignment and once you get on this test on Monday, that is not the time to figure out, it's like, wow, I guess I really didn't know how to do these calculations. So I beg of you, okay, I beg of you, do these calculations as we go along. So here's the story. So you got a satellite. Let me go show out the lights so I can see this a little bit better. So you got a satellite 122 kilometers above the Earth, and that's the only number that you know. Okay, it's 122 kilometers above the surface of the Earth. So I want to calculate the velocity, the orbital period, the centripetal acceleration, and the gravitational acceleration at this altitude. So I want to find out all four of those numbers, only knowing 122 kilometers. Now, but here's the big idea. And this is what you have to understand in terms of the big picture. As this satellite is orbiting the Earth, okay? Number one, it's in a continuous state of free fall, okay? All it's doing is just falling around the Earth like a cannonball shot with just the right velocity as it goes around the Earth. It is not in zero gravity. It floats just because everything within this ship is in a state of free fall. Okay, so get out of your minds right now, oh, things float in space because they're in zero gravity. If they were in zero gravity, they would go flying off in a straight line and they wouldn't even be in orbit. So here's the basis of all these equations, is that centripetal force acting inward is equal to the gravitational force between that satellite and the Earth. That is the biggest idea that you have to get straight, okay? Now, so first off, here's what you're going to do wrong. So Caden, since I can see your smiling face, so what are you going to do wrong with that 122 kilometers?
You're going to forget to add the Earth's radius.
Okay, that's one thing that you're going to do wrong, okay? So that's that distance is here, okay? So but before you can even add in the Earth's radius, what are you going to have to do to those 122 kilometers? What are you going to have to do?
Change it to meters.
Beautiful, okay? So here's what you're going to do. You're going to look at those 122 kilometers and you're going to, oh, there's the radius. And it's going to be an absolute train wreck on this problem. You're going to get times that make no sense. You're going to get velocities that make no sense. Nothing, okay? So I'm going to tell you right now, on almost every problem that you're going to have, not all of them, but almost every problem you're going to have, you're going to have to do some conversion. Hours into seconds, kilometers into meters, something, okay? You're going to have to do some type of conversion on almost every problem. Not all of them, but most of them, okay? So, like Caden said, when we want to try and find that velocity, and that velocity is going to be V equals the square root of big G M over R. Now, there's a couple of things that I want you to look at. This mass, okay, this mass is not the mass of the satellite. I will never, ever, ever give you the mass of the satellite because it doesn't matter. You couldn't put the mass of the satellite into this equation if you tried. It's not there, okay? This is not the mass of the satellite. It cancels out of the equation, okay? So if on a multiple choice question I say, hey, if I double the mass of the satellite, what impact is that going to have on the velocity of the orbiting object? It won't, okay? It's a trick question. It won't change it. There's nothing to do. It has nothing whatsoever to do with it, okay? It's not there. Now, does it take more centripetal force to keep a big, massive satellite like the International Space Station in orbit? Yeah, but guess what? The International Space Station also has a greater gravitational field acting on it, so it all balances out at the end anyway. All right, so here's what I want somebody to do. We got to have this radius, so take 122,000 meters and add that to the radius of the Earth, and let me know what you get. You can type it into the text and just say it. Come on, peeps, we're on a time schedule here. Out of all of you, I'm sure someone can do this calculation.
600, or 6, hold on real fast.
Works, is that you?
Yeah, sorry.
That a girl.
6,400,000.
Oh, no. Give this me in scientific notation, sweetheart.
6.49.
And don't round this thing. Do not round this number. You give me all of these digits. Do not round this calculation.
6.4933.
E to the sixth. Everybody cool with that? We're good. Like I said, when you're finding this radius, do not round this radius. Keep all of these digits and then round when you get to the bitter end, okay? So here's what we've got. So we're going to have velocity is going to equal big G, mass of the Earth, and hopefully you have those numbers stored in your calculator, divided by 6.4933 e to the 6th meters. Now, from yesterday, every velocity that you're going to calculate, whether you're orbiting the Earth or orbiting the Moon, should be something times 10 to the 3rd meters per second. Okay? That's kind of an operating number. If you calculate this velocity and you're getting like 10 to the 6th, 10 to the 7th, you did something horribly wrong. This is my solemn vow. Any orbiting velocity of a satellite is never, ever, ever going to be bigger than 10 to the 3rd. Say, if you ever get an exponent of bigger than 10 to the 3rd on an orbiting velocity of a satellite, it's wrong, okay? This is my solemn vow. On the test, on the homework, whatever, you are never going to get an orbital velocity with an exponent to the 4th. It is not going to happen, okay? So if you get anything other than 10 to the 3rd, you've done something wrong. Okay, so, Wirtz, what did you get as an answer? Or somebody. What'd you get? 5 point what? 5.53?
Yeah.
Times 10 to the 3rd?
Yeah.
I don't think that's right. Did anybody else get anything else? It might be that seems small. The exponent's right, but I don't think that first numbers are right.
You're right, for Kim. It's 7.84.
I like that a lot better, Wirtz. I like that a lot better. 7,840, okay? Because I know it had to be something around like 8,000 meters per second, because that's how fast you have to be going just right at the surface of the Earth. So I knew it had to be something close to that, okay? So now we've got our velocity. Remember this number because we're going to need it later on, okay? So, like I said, that's about 5 miles per second to give you some idea of just how fast that really is. So here's the deal. So we've got our velocity now. So now we need to find that orbital period. So to find that orbital period, I'm going to write this down here. Go with that 4 pi squared r cubed equals big G mass of the Earth times t squared. Okay, this is what you're going to have on your equation sheet, and you have to be able to solve this equation for either r, mass, period. Okay, so this is going to be a test of your algebra skills. Now, I beg of you, when you solve this equation, do not write in all of these numbers and then solve for period. Okay? Don't do it. It is going to be a monumental waste of your time. Writing in the mass of the Earth and big G and the radius and then trying to solve this thing for t. Don't do it. Okay? You're going to spend hours writing down numbers that you don't need to. Okay? Just solve this thing for t. And then when you get done, then put in the numbers, okay? Trust me on this one. Because it's much easier to go, oh, t is going to equal 4 pi squared r cubed over big G mass of the Earth and the square root of all of that. That's much easier to do than writing out all of those numbers and then trying to solve this equation, okay? Solve the equation first, I beg of you. Solve the equation first. Okay, and when you're doing this, I don't even care if you don't even have to write out the value for big G and the mass of the Earth. If you want to, that's fine. I do want to see actually what you put in here for the radius, because that's what's going to change. But you don't have to write out these numeric values, okay? I know what big G is. I know what the mass of the Earth is. You don't have to write those numbers out. If you really want to, that's fine. But you can just leave these in terms of these constants, because that's all you have them stored in as your calculator is anyway. So now your radius we said was 6.4933. e to the sixth. That's going to get cubed divided by big G, mass of the earth. Okay? Now, don't forget, okay? Don't forget to cube this number. Okay? If you don't cube this number, that value of time is going to be off by so much. Okay? You're going to get a ridiculously small amount of time. Also, don't get so happy that you get everything calculated in here that you forget to take the square root of it. Okay? I've seen that happen as well. Don't do it. Okay? Remember, your period in seconds should be something times 10 to the third. Your velocity should be something times 10 to the third. They're easy numbers to remember. ABC, 1, 2, 3. That's going to be the value of the period in seconds. That's going to be the value of that velocity in meters per second. Okay, so works. What did you get from period?
Hold on, just 1 second, step back in.
Okay, all right, dear. I got nothing but time. I'm going to drink my coffee. Come on, Sproles, I haven't heard from you today, man.
What should the exponent be?
10 to the third.
Yes, I got it. Okay.
Okay, what did you get? You're so excited.
5.21 e to the third.
What'd you get?
5.21 e to the third.
E to the third seconds. Now, do me a favor. Take that and divide that by 60 so we know how many minutes that is. Should be around 90.
That's 86.8.
86.8 minutes, okay? So that's about an hour and a half, okay? So if you're in this satellite, that means if you would go, if you could track this satellite, and you had a tracking station here at the high school, that means about every hour and a half, that satellite is going to make a pass over you. So this is like, for example, satellites that they use for weather, okay? So if you want to continuously update, you're going to have a satellite that's going to pass over this region pretty often. So this is about what it takes for the International Space Station to orbit. Okay, it's a pretty near Earth orbit. So here's what I want you to see out of these two calculations. With your velocity, if you put it into a higher orbit, the velocity goes down because you're dividing by a bigger number. Okay? If you're talking about the orbital period, if you boost it into a higher orbit, it's going to increase the amount of time. Okay? So, period is proportional to like the square root of r cubed. Velocity is inversely proportional to the square root of r. So, velocity gets smaller, period gets longer if you boost something into a higher and higher orbit. Okay? Good, we got that. All right, so now remember these numbers, 78.4 times 10 to the third, and that value of, that's the main number that we're going to need is this. So let me kind of get all of this out of the way. Okay, and Wirtz, remember that radius because we're going to need that radius. Okay, so here's the next big thing that we need to find. And if you can do these calculations and feel good about them, that's about 80% of gravitational motion is just getting familiar with these equations. So we got the velocity, we have the period, right? Now we need to calculate the centripetal acceleration. So there's two ways that you can calculate your centripetal acceleration. One is you can use v squared over r, or you could use 4 pi squared r over t squared. Okay? Those are your two choices. So, Suha, which one do you want to use? V squared over r or 4 pi squared r over t squared?
V squared over r.
Beautiful. That's what I would choose because that's going to be a little bit easier. So, I've got that velocity, which we said was 7.84 e to the third meters per second, and that's going to get squared. And then what was that? What was that radius? 6 point. Worth, what was that radius?
6.9433 e to the 6th.
6.9433
E to the 6.
meters. Okay? So, you could do this one if you wanted, and then divide by t squared. Mathematically, this is a little bit more challenging because you got to square pi, and then the radius, and then you got to square the period. Okay? You're going to get the same answer either way. It doesn't make any difference. But I'm with Suha. I would have picked this one because all you have to do is square the velocity and then divide by that radius. Now, before you get an answer, okay? Before you get an answer, let's just think this through. So here's the Earth, right? So right now, if I'm on the surface of the Earth and I drop this 1 kilogram mass, I know it's going to accelerate at 9.8 meters per second squared. Okay? I know that's going to be my acceleration. So at this point, I'm 122 kilometers above the surface of the Earth, right? So I'm further from the Earth. So I've got to figure that when I calculate this value of little g, that number is going to be smaller than 9.8 meters per second squared. Okay? So if I do this calculation and I get something bigger than 9.8 meters per second squared, it's a train wreck. Something has gone wrong. So if you were to look at a graph of radius and gravitational acceleration, so this would be the radius of the Earth. Okay? That's going to be 9.8 meters per second squared. Okay? So as I increase that radius and go further and further and further from the center of the Earth, that gravitational acceleration is just going to get smaller and smaller and smaller. So the biggest value of little g that you're going to calculate, which is the same as your centripetal acceleration, has to get continuously smaller. So what did you get for your centripetal acceleration? 8.85. All right, I like that number. Okay? So we get 8.85 meters per second squared. So what that means is if you're this satellite and you're going around, that's the centripetal acceleration that you are going to experience, which is a little bit less than 9.8 meters per second squared. Notice this isn't zero by any means, okay? You're still under the influence of the Earth's gravity. Now, here's the last thing that we have to calculate. And now we need to calculate little g. So now we're going to figure out exactly what this number is. So when we do this, there's only one way and one way only that you can calculate little g. Okay? So, and that's little g is going to equal big G, mass of the Earth, over r squared. There is no other way to do this calculation. That's it. That is the only way. So, you're going to take big G, mass of the Earth, and then divide that by that radius, which was 6.9433 e to the 6th squared. Okay? And do not forget to square this number. Okay? Do not forget to square this. So, works. Crack these some numbers.
8.27.
No, something's wrong.
Lovely. Okay, let me do it again.
Because these two numbers have to be the same. Either that number is wrong or this calculation of g is wrong. Because they have to be the same number. So one of your two calculations is wrong. Come on, there's a whole bunch of you, and I know you all have calculators. Somebody get me some answers. Don't make me reach through this.
I think it's because the radius is supposed to be 6.4933 e to the 6th, not 6.94.
Oh, okay. Well, that would explain it. 6.4933. Okay, well, let's try those numbers again. Okay, let's go with these numbers and we'll see what we get. I'm glad you all took my advice and all of you were sitting there crunching the numbers. Sproles, did you get an answer?
Not yet. I'm trying to figure out all the numbers to put in.
Okay. Caden?
Not yet, hang on, almost done.
For Kim, does 9.46 sound better
Yes? For which one?
for little g?
Okay, I can live with that.
That sounds better?
That sounds better. Okay, I like that. So let's try that centripetal acceleration where you use v squared over r. About the same, right? Okay? So here's the idea. Okay, and this is the most important thing conceptually that you have to understand. Okay? So I'm going to move down here. So when this satellite is in orbit, okay, you have gravity pulling down, and that's equal to your centripetal force, right? So there's a whole bunch of things that you can set equal. So you can set big G, mass of the satellite, mass of the Earth over r squared, equal. So that's your gravitational force. That also equals the weight, which is the mass of the satellite times G, which is also your centripetal acceleration, which is the mass of the satellite times your centripetal acceleration. So this is vital that you understand that all three of these are equal. This is the attraction between the satellite and the Earth. That equals the weight of the satellite. That equals the centripetal force acting on the satellite. Now, here's what's common to all three of these. The mass of the satellite drops out. It's gone, okay? I will never give you the mass of the satellite because it doesn't matter, okay? But here's what's relevant to this. Little g is equal to your centripetal acceleration. So what that means is if you could put a satellite in near-Earth orbit, the centripetal acceleration is just going to be 9.8 meters per second squared. But here's what you have to understand, is that little g, okay, here, since little g equals big G mass of the Earth over r squared, as you go further and further and further and further from the Earth, little g becomes smaller and smaller and smaller. Your weight becomes smaller. Your centripetal acceleration becomes smaller. So this is why I said when you look at that graph of centripetal acceleration, which is the same thing as g, here's the radius of the Earth. The only thing that can happen as you go further and further and further from the Earth is that that centripetal acceleration and that value of g's just becomes smaller and smaller and smaller. Well, it will effectively go to zero at some point, okay? But it will never technically go to zero. It will approach it, but technically it's like an asymptote. It will approach it, but never reaches that point. Okay, so if here's the magic code. So if I say, hey, what's a certain gravitational acceleration of a satellite? That's going to be the exact same thing as that centripetal acceleration. They're the exact same things. That's one of the most important concepts that you have to get conceptually. Okay. All right. Now, here's the next problem that I promise you you're going to have to do on your assignment and on the test. You mark my words. Okay? So let me kind of get rid of all this so you can see it. Okay. So this is typical of what you're going to have to be able to do. So we found this exoplanet, right? And we've made the observations with the telescope. And we have an orbital period of 20.5 hours. Okay, so that's how long this is going to take to go around. And a radius of 3.68 times 10 to the 6. Now, let's talk about this radius. Unless I tell you that that's the distance above the planet, like I did on that first one where I said that satellite was orbiting 122 kilometers above the Earth, if I just tell you this is the orbital radius, that is the distance from that moon to the center of the Earth. So unless I specifically tell you that that's the distance above a planet or above a moon or something like that, unless I specifically tell you that that's the distance above, you just assume that that distance is from the center or from that moon already to the center of that planet. You don't have to do anything to it. So unless I listen to me, unless I specifically say that's the distance above, you just assume that that radius is already measured from the center of that planet out. Now, here's the cool thing about this. When we figure out the mass of Jupiter, Saturn, whatever it is, we have to make observations on the influence that gravitational field has on different objects. So in this case, we're going to make an observation of what's going to happen about this moon as it's orbiting around it. So there's only one way that you can solve this problem. And you've got to start with that Swiss Army knife equation and go 4 pi squared r cubed equals big G mass times t squared. Okay, that is the only way that you can solve this problem. So you've got the orbital radius, you have the orbital period, you know what big G is, the only thing you don't know is this mass. Okay, that's the only thing that you don't know. Now again, this is not the mass of the moon. This is the mass of the planet that's orbiting. This mass will always be what's at the center of that orbit. So I'm going to get mass by itself, so I'm going to have 4 pi squared r cubed divided by, so since we're going to be dealing with r cubed, and that's kind of the pirate thing, fourth block yesterday, really liked this one, so hold on. Since we're going to be dealing with r cubed, it's kind of a pirate thing. Hold on. R. How cool is that? R. It's Talk Like a Pirate Day. Okay, so hopefully the pirate hat and everything isn't too distracting. All right, and it's kind of cool, like I can put my hand like through my hat and it just disappears. Okay, hours of entertainment fun right there. Okay, all right. I wish I could hear you all laughing because I know you all are laughing hysterically just at that image right there. Okay, all right, so here's the deal. So we got r cubed, and that's going to equal the mass. Now, somebody tell me what you're going to do wrong with that 20.5 hours. What am I going to do wrong with that? What am I not going to do?
Convert it to seconds.
Yeah, you're not going to convert it to seconds. You're going to look at 20.5 hours and you're going to go, oh, I'm going to put that number in right there. And you are going to get an answer bigger than the mass of the sun. Okay? Literally, trust me, you will get an answer bigger than the mass of the sun. Okay? Maybe borderline black hole kind of mass. Okay? I beg of you, if you're just going to randomly write down numbers and not pay any attention to the units, this test is going to be an epic failure. Okay, I'm going to tell you this right now. You have to pay attention to the units. So, you can have 4 pi squared, okay, and then you have your radius. You don't have to do anything with that. Okay, that's cool, right? You don't have to do anything with the radius because that's already in meters. Don't worry about it, it's good. Now, I've got G, 6.67 e to the negative 11th. Now, I'm going to take the 20.5 hours, and 1 hour is 3,600 seconds. And then I'm going to square that. don't forget that this is t squared, okay? Because I've seen this happen. You get so excited that you converted hours to seconds. It was like, oh, gold star for me. Cool, I converted hours into seconds. But then you forget the square, okay? That's the other thing that's going to go south, okay? So, somebody get me an answer. And I promise you, you're going to do a problem like this on the test. You mark my words. You're going to have problems like this on the assignment. You're going to have a problem like this on the test. You mark my words. What, Wertz?
The radius.
Huh?
Tell me the radius, I can't see it.
It is 3.68 times 10 to the 6th.
How big should the number be?
I think it's in the low 20s if I remember right.
Okay.
Yeah, I think it's around 10 to the 22nd, 10 to the 23rd, just ballpark in the order of magnitude. And like I said, if you are sitting there in bed and you are not trying to do these calculations, I'm telling you, this assignment is going to be an absolute train wreck.
Does mid-20s work?
Yeah, probably. What'd you
I
get?
got 4.00 e to the 26th.
No, I think that's big.
Oh.
Bergkamp,
What?
I got 5.42 even the 21st.
That sounds better. Sproles, you might try and crunch that again and see if somebody else gets this. I think, out of memory, I think this is right.
I didn't square the second, that's why.
What did I tell you to do? What did I tell you to do? Square the seconds. What did you not do? Oh,
Hey, at least I'm doing it.
I know. And Sproles, I admire you for that.
So I got like 1.9 e to the 41st, but
Okay. Okay. Caden, this is the perfect example. So, that would be like a supermassive black hole. Okay? I mean, that wouldn't just be the sun. That would be a supermassive black hole. Okay? Like, this moon would be completely consumed within this black hole. Okay? So, Caden right now, and again, I'll give Caden credit. At least he's doing this. All right? You got 10 to the what?
I got 10 to the 41st.
Yeah. Yeah, that's that's literally like that's like about 1,000,000 times more massive than the mass of our sun. Okay? It would be a complete and total black hole. So this is why you want to be
Bergkamp,
Huh?
I got it right.
what?
I squared the second, then I got it right.
Okay, you got that same answer? Okay, Caden, you got to figure out what went south with this, man, because that went way south, all right? I mean, this is
Did you
like,
have parentheses, Caden?
the black pearl, she's got sucked into the bottom of the black hole, right? So, that would be an absolute train wreck, man, okay? Absolute train wreck. But this is why you want to be able to look at this and go, oh, okay, 10 to the 6th, that's 10 to the 18th, right? I got 4 pi squared, that'll give me roughly 10 to the 19th. So up here, my exponent is roughly 10 to the 19th. Down here, I got, this is like 2 to the 3rd, so I'm going to square that, that gets me 10 to the 6th. 10 to the 6th times 10 to the negative 11th gets me 10 to the negative 5th, okay? So I got 10 to the 19th divided by 10 to the negative 5th that gets me like 10 to the 24th, and that's a very, very crude estimate. So that's why if you just look at those exponents, Caden, you would have realized like, wow, there's no way it's that big. Okay, so let's work one more, and then you'll have a pretty good idea on how this deal is going to play out. So here's the last big problem that we need to work. And if you can do this one, then we're going to be doing okay. So here's this moon, here's the radius, 1.40 times 10 to the 5th meters. And we know that, so we've landed on the moon, and we've set up our little pendulum, or we've done something, and we figure out the gravitational acceleration is 1.22 meters per second squared, which isn't very big, okay? Gravitational acceleration on our Earth is 9.8 meters per second squared. This is a lot smaller. So when you would drop something, it would fall it would accelerate very, very slowly. So there, I want to figure out two things. What's the mass of the moon? And then what distance from the center of the moon so that a 1 kilogram mass weighs 1 Newton. Okay, so let's tackle this. What's the mass of the moon? So, words. How can I find the mass of the moon? What equation am I going to start with? It's my rap name. Little G the pirate. Talk to me, words.
I'm sorry, my dogs are fighting, but it's the little G.
I'm sorry, I didn't mean. Okay. All right.
G will get little G, right?
Okay, we get it. The dogs are fighting. Okay. Yeah, that's right. Now, here's what you have to remember. Don't look at this and read further down in this problem and go, oh, that's 1 kilogram. That's what I'm going to put in here. This is not the mass of what is falling. This is the mass of the moon, or what it's falling towards. So, as Wirtz correctly predicted, we're going to use this. So we need to get little m by itself. So here we go with the pirate. So it's going to be r squared divided by big G, boom. There's going to be my mass. Okay? No worries right there. So here's what we've got. So we're going to have little g, which we said was 1.22 meters per second squared. We got the radius, 1.40 e to the 5th, and that's going to get squared. And then we're going to divide that by big G. Now, Caden, let's get an idea of what this answer should be. So I got 10 to the 5th, that's going to get squared, so that's going to give me 10 to the 10th. G is 10 to the negative 11th. I move that up, I get 10 to the 21st. So I got to figure on a rough estimate that this mass is going to be something around 10 to the 21st. Just a ballpark estimate. Okay? So help me, if you get a black hole mass again, I don't know what I'm going to do. I'm going to sick Wirtz's dogs on you. How about that? It's like, go get it! Grr! Maybe they're fighting because I'm saying grr a lot. Maybe that's why. That might be my bad words. Or maybe they just don't like physics. Or maybe it's the pirate hat that's kind of flipping them out. I don't know. Okay, so... Okay, all right. 30 years of teaching on 2 continents. That has never been an excuse I've heard. Sorry, my dogs are fighting. Okay, all right, cool. So, what did you get as an answer? Caden, here's your chance to redeem yourself. 3.59 e to the 20th. Caden, are you good with that? Or are you reluctant to answer?
I can't see the problem.
Oh,
I couldn't either.
my bad. Can you see it now? If you can't see it, like say, hey, Burkamp, move.
Yep, that's what I got.
Okay, fantastic. All right, so we're good. Now, we have one problem left, and then we'll be finished with this part. Now, here's like a conceptual thing. So I want to know what would be the distance from the center of the moon out to this point so that a 1 kilogram mass weighs 1 newton. So here's the main idea, is that if you're standing on the surface of the moon, a 1 kilogram mass would weigh 1.22 newtons, because I would take 1 kilogram times 1.22 meters per second squared, and I would get 1.22 newtons, okay? So what it would weigh if you were on the surface of the moon. So I want to know how far I have to go so that basically I want my value of little g to drop to 1 meter per second squared, so that when I take 1 kilogram times 1 meter per second squared, I get 1 newton, okay? So I'm going to take this equation. I want little g to be 1 meter per second squared, because that's, so when I take 1 kilogram times 1 meter per second squared, I get 1 newton. I want this to be 1. I know what big G is. Now I know the mass of the moon. Now I want to solve for r. So now I need to solve this equation for the radius. Okay, that's what I need to do. So I'm going to take, if I solve this for radius, so I'm going to multiply by r squared and divide back. So r is going to equal the square root of big G m over little g. So I got big G, that mass is 3.59. I'm going to write that up there, 3.59. That was horrible. E to the 20th divided by 1 meter per second squared. Now, do not put in 1 kilogram here. That is not what we're talking about. This mass is not the 1 kilogram. That mass has to be the mass of the moon, the mass of the earth, whatever that is. Okay? Now, you've got to figure that when you get this radius has to be bigger than 1.40 times 10 to the 5th. Because at 1.40 times 10 to the 5th, you're right here. So this answer has to be bigger than 1.40 times 10 to the 5th. Okay? It has to be bigger than that. Because that's at 1.22. So, did somebody get me an answer?
I got 1.55 e to the 5th.
I like that. There we go. So if you can do these calculations, you're going to be good. Now, like I said, the beauty of this assignment is that you only have 4 equations to choose from. You have the orbital period, you have the velocity, you have little g, and that big one, F equals big G, M1, M2. Now, I'm going to run out of time. When we get finished, I'm going to keep teaching and explain how number 10 is going to work, okay? So, number 10 is this big calculation of Lagrange problems, and I'm not going to have time in this session because I only have an hour to work through this. So, I will explain number 10 here in just a second. So when I send out the YouTube video, I'm going to send out this whole thing again, and when I send it out, I'm going to tell you to start watching it at a specific point if all you want to see is how to work number 10. So I will have that time stamped, and I will say, hey, if all you want to see is this question about the Lagrange points, start there. So, and it's going to be cool because I'm going to be talking about how space and time is a fabric. I'm also going to go out in the hallway and do I've got the hallway laid out like on a relative scale that you can see how far away the distances of the planets are if you scale that down to the hallway from the commons down here. So I'm going to put all that into an additional video that I'm going to tack on to the end of this. Okay, so and I will tell you specifically, hey, this is when you need to start watching this. So, this assignment, which is on this green sheet, okay, if you don't have this green sheet, I'm gonna send out this as an addition when I send out the YouTube videos. But I think everybody should have this. If they're not, like I said, I'll send that out. So, let me give you some hints on some of these. So, like on number 2, okay, so let me give you a hint on how you're going to start number 2. So you've got 2 identical spheres separated center to center by 1-2 meters, experience a mutual gravitational force of 1 times 10 to the negative 4th, compute the mass of each sphere. So what's happening on number 2 is that here's a mass, here's another mass, and here's the whole key to this, is that they are identical, okay? So I'm going to let this have a mass of x, okay? I'm going to let this have a mass of x, okay? I don't know what they are. And the reason that I'm going to let them both be x is because you're told that the masses are identical. Now, if I said, oh, hey, this mass is twice that of the other one, then I would let this be 2x. If one mass was 3 times the other one, I would let this be 3x, okay? But since they're both identical, I'm just going to let them both be x. So, you've got F equals big G, M1, M2, divided by D squared. So, what you have is that I've given you the force, you know this number. You know how far apart they are. You know this number. You know what big G is. The only thing you don't know are these. Now, here's what you have to watch. This is going to be x, and this is going to be x. Now, I have to point this out because if I don't, this is about what a third of you will do. When I take x times x, do I get 2x or do I get x squared? Words, what do I get? 2x or x squared? Beautiful. So this is going to be x squared. So what you need to do is you need to solve this equation for x. Multiply by d squared, move g over here, take the square root of that. Okay? When you get to number 8, okay? When you get to number 8, here's the visual. So, here's the moon. The Lunar Command Module is 72 kilometers. That's 72 kilometers above the moon. And then I give you the radius of the moon to be 1738 kilometers. So, the orbital satellite is 72 kilometers above the moon. Here's the radius of the moon, 1,738 kilometers. So you're going to have to do 2 things. You're going to add these 2 numbers together to get them as your radius, and then multiply by 1,000 and get that as meters. So on number 8, you need to add these 2 numbers together, multiply by 1,000, boom, there's your radius. When you get to number 3, okay, so when you get to number 3, I'm asking you, how far from the Earth would you have to be so that a 1 kilogram mass weighs 3 newtons? Okay, so I give you this hint. So if I have this 1 kilogram mass right here, it weighs 9.8 newtons because I take 1 kilogram times 9.8 meters per second squared. So basically what I'm saying is that how far would I have to go so that this experiences an acceleration of 3 meters per second squared? So on number 3, you can do that problem just like we did. Okay? Little g is going to be 3 meters per second squared. This is big G. Use the mass of the Earth. Do not use 1 kilogram. Use the mass of the Earth. Solve this for R. Okay, so time is up. When I send out this video, I'm going to add on that additional stuff for the Lagrange point. And I'll also include that video on the relative size of our solar system out there in the hallway. So, tomorrow, we're just going to go work through this assignment and get ready for that test on Monday. So, all right, kids, be safe, stay home, avoid people. All right, see ya. Yes, ma'am. Monday. All right. Okay, so here's the deal. Hello? So, after Newton published his works, that F equals big G m1 m2 over d squared, we understood the effects of gravity, but we really couldn't visualize what actually caused gravity. And so, when Einstein did his work on theory of relativity and special relativity, so he viewed time and space as like a fabric, okay? So imagine that this spandex is like space and time. So you can actually model Newton's laws of motion. So if I take this small little marble and I roll it across, notice that that marble pretty much just travels in a straight line. So because space and time isn't warped and there's no outside forces acting on it, it just goes back and forth in a straight line. So imagine this is like a massive object. So let's say this is like the sun, okay? So I want to put the sun at the center of our solar system. So now what's happening is that sun is creating like a warp of space and time. So now when I roll that marble, notice that that marble is now following a curved path. And notice that it always ends up at the bottom of this gravitational well, because that's the lowest possible energy state. So when this thing is going by, gravity is just making space and time warp, so it's following that curved surface. Now, there's something very subtle. You can also do this in terms of Newton's third law. Newton's third law says for every force there is an equal and opposite force. So if you focus on this one right here, you'll notice that when it goes by, you get a little bit of a wobble, okay? So when that goes by, okay, this one wobbles just a little bit, because even though this is much smaller, it's creating its own warp in space and time, and that's what's causing this marble to move as well. It doesn't move as much because it's a lot more massive. So the smaller one has a much greater acceleration because it has a lot less mass. Okay. Now let's talk about going to the moon, which is going to be this question on the Lagrange points. So imagine here's the Earth, okay, this is this deep gravitational well. And then here's going to be the moon, and it's going to be this more shallow gravitational well here. Let me make sure you all can see that. Okay, you can. Oh, hold on. Okay, so basically if we want to go to the moon, here's your sequence. You launch, you let this thing orbit the Earth a couple of times, make sure everything checks out. You fire the engines, you coast towards the moon, you get caught in its orbit, you orbit around the moon, boom, you fire the engines, you come back, you land on the Earth. So the Earth is much more massive. It has a much deeper gravitational well than the moon does. So what we're going to do is we're going to talk about these Lagrange points. So if I fire the engines after I orbit the Earth, and I'm not going fast enough, hold on, that was too fast. If I'm not going fast enough, the only thing that's going to happen is that this thing is going to go out, and then it's going to start to come back down. So this is on your lecture notes, but one of the most important things when you're talking about leaving a gravitational field is what's known as the escape velocity. So the escape velocity is how fast you have to go to leave a gravitational body. So it's like, if you can visualize this, so if I throw this thing up in the air, even right now, oh, it comes back down. If I throw it faster, it goes up higher. If I could throw this little marble fast enough, it would leave the gravitational field of the Earth and never come back. So you can visualize this in terms of this gravitational well. So if I just give this a little bit of velocity, it's going to roll back down. But if I give it enough velocity, then it's going to leave the gravitational well of the Earth and then get caught in the gravitational well of the moon over here. So the Lagrange point, there's going to be two of them that you're going to calculate. One of them is here between the Earth and the moon, and one of them is out here on the other side of the moon. So, to visualize this in terms of space and time, so imagine that I put the spacecraft halfway in between the moon and the Earth. Now, if I just put it right there, notice that it's going to fall back towards the Earth. Because at that point, because the Earth is more massive, the net force is going to be pulling it back towards the Earth. The moon is pulling on it, okay, but not enough to make it go in that direction. Now, if I get too close to the moon and let go of it, then it accelerates to the moon. So if you can visualize the Lagrange point as being like the crest of this wave, or the crest of this hill in between these two gravitational wells. So if I find that point just right, hold on, right there. So at that point, right here, this marble, or the spacecraft, is feeling a gravitational pull towards the moon, and it's also feeling a gravitational pull back towards the Earth. But at that point, it's like a tug of war. So you have the moon pulling it this way, the Earth pulling it this way, and it's like an equal pull. There's no net force. You're in the gravitational field of both objects, obviously, but it's like an equal pull. So what that means, what this Lagrange point represents, is if you could look at this from an orbital path, and the moon would be orbiting the Earth, what would happen is that spaceship would stay exactly at that point. You would not, if you could stop that spaceship and put it right there, it would stay completely locked between the Earth and the moon, and it would go around like this. You're just going to be riding the crest of that gravitational hill in between these two wells. So, now, after it crosses that point, okay, then it's going to begin to accelerate towards the moon, because now that gravitational well is deeper. The net force is going to be pulling it towards the moon. Now, I don't want you to think this. Don't go, oh, now we've left the gravitational pull of the Earth. No, the Earth is still pulling on it, okay? But the dominant force now is pointing towards the moon. So don't think when, oh, you're orbiting the moon, you're outside the gravitational field of the Earth. No, the Earth is still pulling on it. But the moon is a much stronger force at that point. Now, when you get into like binary stars, for example, create weird distortions in the space and time. So now you have like two different gravitational wells. So now when you look at things that orbit binary stars, okay, then you kind of get this weird figure 8 shapes going on. By the way, you can just play with this for hours. So, but here's what's going to be important. No matter how many times you do this, no matter where you start it, oh, that was a good one, okay? They always end up in the bottom of a gravitational well, because that's the lowest possible energy state. So when you get binary stars, you get some really funky distortions of space and time. So, okay. Yeah, right. Okay, one more. Oh, that was a good one. Oh, I thought I was going to stop right in the middle for just a second. Okay, all right. So I'm going to stop this, and then I'm going to show you how to work problem number 10 with the Lagrange point. So I'm going to stop this for a second. Okay, so let's talk about number 10 and the Lagrange points, okay? So what you've got is that here's the Earth, here's the moon, and you want to find these 2 points, okay? Where basically what those points are, and there's actually 6 of them. We're just going to find the first 2. So the idea being is that that's the point where you could stop this thing in its orbit and it would remain locked right there. So this one's conceptually the easiest one to look at. So we want to find the point where the gravitational pull on the Earth is equal to the gravitational pull on the moon, okay? What we want to do. So if you look at this and go, okay, that force is going to be big G. I need the mass of the Earth. I need the mass of the Lunar Command Module. And then I need this distance here, which I don't know what that is. So I'm just going to let that be x squared. Okay? Now, that has to equal big G, the mass of the moon, times the mass of the Lunar Command Module, and this distance. Now, I don't want two different variables because that's just going to get real ugly. So, on the problem, you're told that this entire distance here is 3.844 times 10 to the 8th meters. So the entire distance from the moon to the Earth is 3.844 e to the 8th. So here's how this is going to play out. If you're going to let this distance be x, okay, then whatever's left over is 3.844 e to the 8th minus x. So this is what's going to be left over. So over here, I'm going to put this as 3.844 e to the 8th minus x squared. Okay? Now, here's the beauty of this. This looks horribly daunting at this point. But look what happens, and this is why you work with variables. I can cancel out these big G's because they're on both sides, so I don't have to worry about that. I also have the mass of the Lunar Command Module. That cancels out. So again, on number 10, there was a reason I didn't give you the mass of the Lunar Command Module, because you don't need it. So I'm going to drop out these G's, and I'm going to drop out the mass of the Lunar Command Module. Now, at this point, I hate fractions. I'm going to cross multiply. I'm going to take the mass of the Earth times this, and that's going to equal the mass of the moon times x squared. So I'm going to have the mass of the Earth times 3.844 e to the 8th minus x squared is going to equal the mass of the moon times x squared. Now, I've given you the mass of the moon. You have this number. You all know the mass of the Earth. I want to get x squared by itself, okay? So I'm going to divide by the mass of the moon, okay? Now, if you do that, this is going to leave you with x squared. If you take the mass of the Earth and you divide it by the mass of the moon, you get 81.35. Okay? Now, what this means is that the Earth is 81.35 times more massive than the moon is. Okay, so just on a straight division, that's how much more massive the Earth is than the moon. So, we want to solve for x. Now, there's two ways that you can do this. I'm going to explain the first one, but I don't recommend you do this because it's a god-awful amount of work. Option number one is that you expand this binomial. Okay, just like if you have 4 minus x quantity squared, you'd have 16 minus 8x plus x squared if you remember back to your FOIL method with binomials. Okay? So you would expand this, then you would distribute the 81.35 over all of that, then you'd move x squared over here, and then you'd have like the form of x squared and x and a whole number. And then you'd plug that into the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. It's a god-awful amount of work. And if you really want to work the most intense quadratic problem you've ever had, you can do it that way. But there's a simpler way. The simpler way is that we're just going to take the square root of both sides. Okay? So, here's going to be the key. If you take the square root of both sides, you get the square root of 81.35, which is, and this is going to be important, that's plus or minus 9.02 times 3.844 e to the 8th minus x is going to equal x. Okay? Now we don't have to do the quadratic. So, but you're still going to have to work this problem twice. Okay? So, here's what you're going to do. Situation number 1, you're going to take a positive 9.02 and you're going to distribute it over this. So you're going to take, don't even worry about the negative sign for now. You just take 9.02 times this, and you're going to end up with negative 9.02x. It's going to equal x. Then you're going to move this x over here, and then you're or whatever, however you want to do it, but you're going to get your x's on one side, and you're going to get your numbers on the other, and you're going to solve for x. So you still have to distribute this. You still have to combine your x's, put your x values on one side, put your numbers on the other, solve for x. It's the first time. To get the second root, you're going to take negative 9.02. So you're going to take negative 9.02 times this, negative 9.02 times the negative x. Now that's going to get you positive 9.02x. It's going to still equal x. Then, after that, then you're going to do the same thing. You're going to put all your x's on one side, all your numbers on the other, and that's how you're going to get your two possible roots. So if all goes well on number 10, both of these, L1 and L2, are going to be 10 to the 8th. Okay? L1 is going to put you between the Earth and the Moon. So L1 has to be less than 3.844 times 10 to the 8th. That's going to get you L1. L2 is going to put you out here somewhere on the other side. Okay? So that's what you want to look at. Let me give you a hint. When you do number 16 on this assignment, number 16 is just old school, that equation, v squared equals v naught squared plus 2ad. Okay? It has nothing to do with escape velocity, nothing like that. You're just going to go old school. When you get to, speaking of escape velocity, so when you get to number 18, it talks about escape velocity. That equation and that definition is in the back, is on the last page of those lecture notes that you have. It's the one that's stapled together. It's that big set of lecture notes. If you don't have it, I'll send that out again. But that's where you're going to find that escape velocity definition. So, escape velocity is how fast you have to go to like escape a gravitational wave. Okay, so tomorrow we're going to talk more about this. I'm going to go out now into the hallway and I'm going to lay out kind of the relative size of our solar system. So, we'll stop this again. Okay, so here's what we've got. So I'm here in the entrance going down into the commons, so you kind of get an idea of where I'm at in the hallway. And what I did is that I laid out a relative scale saying that this entrance right here is the face of the sun. And then I've got all the planets laid out. I did not include Pluto because it would be so far off the scale that it's really not something that's practical. So what I've got is that, and we're going to start with like the solid rocky planets first. So here's the surface of the sun, right? So right close, you got Mercury. Then you've got Venus. And then you've got the Earth, okay? Even brought the globe out. And then you have Mars. So these four rocky interior planets relative to the sun are pretty close to each other. Now, if you look on down the line, so that, and I'll walk this, so that first trash can is going to be Jupiter right there. Then on down the line, we'll zoom in a little bit, okay? Then the trash can that has the American flags on it, that's going to be Saturn. So, and then the next one, way down there, where you have like the bowling ball, and then way down there, and let me zoom in on that, is Neptune, okay? That little hold on. Pumpkin right there, that's Neptune. So on just kind of pan out and around. So if that's Neptune, going back, boom, there's the sun. So imagine that you're in charge of trying to send a probe all the way to Neptune, which is way down there. Okay? So that right there. And Neptune is moving, and you're launching from an Earth that's spinning on its axis. So we're going to start here. You got Mercury, Venus, the Earth, kind of some perspective. There is the school store. And then you have Mars, all right? So there's your interior rocky planets. And then we're going to walk along. And then we're going to hit Jupiter. Okay, so, oh, there it is. There's Jupiter, right? So you can kind of get a scale. So let me kind of look back towards the Earth, and there's the Sun. Okay, so kind of get an idea of scale. And then we're going to walk out here towards Saturn. And here we are at Saturn. So again, we're going to look back, right, on some scale. So there's Jupiter, there's the Earth, boom, there's the Sun. Okay. So now we're going to keep going and going and going and going and going. We're going to walk. We're walking, and we're talking, And now we're going to go all the way out here. And here is Uranus, okay? So there's Uranus, okay, right? And look back, and now we're looking back towards the sun, and now kind of some perspective. There's our Earth, okay? So if you were on Uranus looking back, the Earth would appear as just this tiny little dot. So now we're going to go all the way out here to Neptune, okay? So to kind of give you some perspective, we're walking down here towards the hallway where you turn to go to my room, okay? So there's the fish tank going down to my room, okay? And then here you are at Neptune, okay? So this is kind of looking at it from the opposite perspective. So if you're out here on Neptune, and, oh, got out of focus. Then there is our home planet, and there's the sun. So again, I just kind of do this so you get some perspective on scale. And there we go. Okay, so hopefully that kind of gives you some perspective just on the great distances that are involved on our solar system.